Good morning, good afternoon, good evening, mammals. I'm going to start off with a super short video that I'm not even going to tag with an NTI date for starting our very next unit. I received word from on high that next week I'm not supposed to do, not next week, the week after spring break, I'm not supposed to do any new material. So we're going to save kind of our summative FRQ on kinetics for that week, since technically I won't be doing any new material. And I'm going to go ahead and start a little bit this week with our last unit, which is kind of a grab bag assortment of some leftover topics, mainly going into a little more depth about some topics that we introduced in the first unit. And the first one that we're going to look at is some trends on the periodic table, like electronegativity, and going into a little more detail about those. But before I can do that, we need to think about how the electrons arrange themselves in more depth than just a standard electron configuration. So I'm going to introduce a way of showing electron configuration that is called orbital notation, and it'll only take me a second. Recall that our orbitals are these three-dimensional arrangements. So this is an s orbital, and there's only one s orbital because since this is basically a point, basically like 0 dimensions, this infinitely small sphere, there's only one way to arrange them, and it's the same no matter any which way that you look at it. A p orbital, on the other hand, is sort of this one-dimensional linear shape. So there are three ways that we can align a p orbital. We can align it along each of these axes. So I've drawn this one aligned along the z-axis. The other p orbitals would be the same shape aligned along the y-axis. Maybe I'll sketch one in there if it doesn't get too messy. So aligned along this y-axis, or aligned along the x-axis. So that's why there are three unique p orbitals, because there's three different ways that we can arrange this shape. The d orbital is kind of a two-dimensional shape because these pair of lobes define a plane. So this plane can be arranged actually 5 different ways. In this configuration, I've drawn it aligned with the XZ plane. I could also rotate this so it's aligned with the XY plane and then with the YZ plane. There's also two other variations where it's aligned, instead of kind of being 45 degrees offset of the axes, where it's aligned along with the axes. But it's not really important for you guys. Just know that there's like 5 different ways to arrange this one. So I've got 5 different d orbitals. I'm not going to do this with f orbitals because they're too difficult to draw on a two-dimensional surface because they're a three-dimensional shape. But just run with me that there would be 7 different ways to arrange an f orbital. In summary, we have one kind of way to arrange an s orbital, 3 kinds of ways to arrange a p orbital, 5 to arrange a d, 7 for an f. Within each of these orbitals, they can hold 2 electrons. Electrons being a moving electric charge, they generate a magnetic field. So when you put 2 electrons into the same orbital, they're going to have to occupy opposite magnetic states, kind of like north and south pole. So that limits us to 2 electrons for each of these orbitals. And this is where we get that an s orbital can hold max 2 electrons, a p-type orbital can hold max 6, a d-type can hold 10, and an f can hold 14, because we've got 1, 3, 5, and 7 different ways to arrange them times 2 magnetic states. What we're actually showing in this orbital notation is how those magnetic states arrange themselves. So I'm going to start with a really simple one to show how we do this. I'm going to use carbon. If you look at its location on the periodic table, you'll see that this is its electron configuration. And so that means I have one 1s kind of orbital. I have one 2s kind of orbital. And the p's have 3 kinds of orbitals. So these are the orbitals that I need to use, and I'm going to start assigning electrons to them using little arrows to indicate their magnetic spin state, the sort of north or south pole like before. So when I put 2 into this s orbital, I draw them like this to indicate opposite spins. Now I'm going to do the same thing with the 2 in the 2s. When we get to the 2p now, I've got some choice because I have 3 orbitals open to me and 2 electrons to put in them. The correct way to do that is to basically not pair them unless you have to. This is called Hund's rule. And it exists because electrons repel each other. So if they aren't forced to be in the same orbital, then we don't put them there. So that means if I extended this to nitrogen, 1s2, 2s2, 2p3, spin up, spin down, spin up, spin down, and I get to this orbital, spin up, spin up, spin up. I don't have to pair any of those. When I go on to oxygen, so if I change this to oxygen, 2p4, now for the very first time, I would have to pair them because I've got 3 empty spots. Since electrons repel each other, I'm not going to put them there unless I have to. This leads to the explanation for some exceptions to this principle. In the past, you actually had to memorize these exceptions. Now, I think you would only have to offer an explanation as to why the exception exists. So if I consider, I believe this is manganese. I don't have my periodic table in front of me. If you followed the pattern, this would be its electron configuration. For brevity, I'm not going to draw out all of these. I'm just going to draw out kind of what we would write as the noble gas configuration. We'd be putting this guy as argon 4s2 3d4. So there's my 4s orbital. My D has 5. I'm going to fill my 4s. So manganese is an exception to this. If you'd ever noticed this, kind of some of these while you're over on the periodic table, I've got these guys that are paired right now, and I have an empty spot here. Because the 4s and the 3d are very, very close in energy level, this guy can actually go there. And it just minimizes the repulsion a little bit by putting it in this vacant d orbital, and since the energy difference between the d orbital and the 4s orbital are close enough, this can occur. Don't extend this, don't try and make this happen whenever you see fit. Only talk about exceptions to this pattern if it's presented to you as such, because the actual configuration is 4s1 3d5. So don't go off doing this on your own. These are exceptions to this principle and generally don't happen. This would just be the explanation should you come across one and have to explain it. So I'll be referring to these when we start talking about some of these other patterns in more depth on the periodic table, and it'll just be a kind of visual way for you guys to understand what the electrons are doing. So I'm going to wrap it up for today. As always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.